Welcome to Amp Life, the #1 podcast for amputees, hosted by an amputee, and brought to you by Dilatory Orthotics and Prosthetics, located in Pittsburgh, Pennsylvania. I'm the Brian Moe, the social media advisor for Dilatory, and I also happen to be a below-knee amputee. Let's get into today's episode. How's it going, everyone? My guest today is the Interim Dean of Florida International University's College of Engineering and Computing and the Chair of Biomedical Engineering at FIU, Dr. Ranu Jung. Dr. Jung, welcome to Amp Life.
I'm delighted to be on the show.
Share with us a little bit about your role at FIU.
As you said, I'm a professor of biomedical engineering at FIU. I joined FIU in 2011 as the chair of the Department of Biomedical Engineering. It's a department which is a quota-endowed department with about 500 students, and some of the faculty do research in the neurotechnology area. So I have been helping guide and that whole program. And since 2015, I have also stepped in as the interim dean for the College of Engineering and Computing at FIU. And the college is about 6,000 students and has multiple schools and departments. So as a professor, I do research, I do teaching, and I also do service. And then as an administrator, I am responsible for making sure that things are moving forward as we educate the next generation of students.
Okay, very good. So how did you come to be involved with the Adaptive Neural Systems Laboratory?
So the lab is my research lab, and I established it, and it has grown out of my long-term engagement in research for studying neural control of physiological systems and motor systems and developing devices to support the repair and recovery of neurological disability or trauma. I came from Arizona State University, where I was previously, but all the way back to even the time when I was doing my doctoral work, my interests have been in motor control and in the neural control systems. So it is the culmination of some of that effort for over many years that has led to the development of this research lab.
Okay. What type of research does the lab do?
So, as you know that we have been granted an investigational device exemption by the U.S. Food and Drug Administration for a first-in-human trial with we call a neural-enabled prosthetic hand. So with regards to the research that the lab is doing, a major focus of our lab has been the design and development of this system for upper limb amputees in particular. And then obviously we have taken the development of that and now are working towards a clinical trial or early feasibility clinical trial of the system. Other work that we are also working on currently is developing a approach to control stimulation of the diaphragm, so pacing the diaphragm with the goal of being able to provide an appropriate diaphragmatic pacing to people with spinal cord injuries. We also look at design of new kinds of electrodes to interface with the different nerves in from coming out of the spinal cord, the spinal roots or other nerves, in order to make these links between the devices and the person, so a biohybrid system. And finally, some of the studies we are doing is looking and mapping the brain under different activities and under different conditions. So we're looking at the EEG patterns, and we are also doing something called functional near-infrared. NIRS, so spectroscopy, so looking and imaging the brain using FNIRS. So overall, the goal is projects to develop, design devices to improve functionality and restore functionality for people with disabilities that may have occurred because of neurological disease or trauma. That, I think, in general, that is the main focus of the lab.
Okay. So you mentioned that you've been granted the exemption by the FDA to start the first in-human trial with the neural-enabled prosthetic hand. When did you first begin research on this system?
So this, the project itself started in somewhere around 2006, 2007. So we had initially, we put in a proposal to the National Institutes of Health to seek funding for the project back in 2006. We got the funding in 2007. So it's been almost 10 years. So since we have been working on this project for a long time,
Okay. So what are some of the expectations that you have for what this system will be able to do for upper extremity amputees?
So what we expect is that we will be able to, integrate versatile sensory-enabled artificial limbs. So if we have artificial limbs that have got sensors that could pick up force, hand opening, things like that we should be able to integrate that information with the intact sensory motor capabilities of the amputee. So, for example, we want to restore the sense of touch and hand opening to the user. So, so you have got, if you have a prosthetic hand with the appropriate sensors to touch, to get force information or hand opening, we expect that we will be able to take that information and communicate it as seamlessly as possible to the user amputee by interfacing with their nervous system directly. And so this might help the person with the restoration of sensation that may help with the improved motor performance, for example, grasping things or picking up a grape without crushing it, even if you don't look at it.
Okay. So, as you know, there are numerous state-of-the-art prosthetic hands already on the market. How is the NEPH any different from those devices?
So keep in mind that, of the devices that are on the market, most prosthetic hands currently don't have any sensors built into them for picking up sensation. So that's the first thing. And the second thing is, even if you think about the myoelectric hand, which you have EMG control of it, there is nothing that is giving the sensation back to the person, right? So if you had if you had a cable system, then you would still get some feedback, by mechanical feedback. But for example, with the myoelectric hand, you are not getting sensory feedback. So what this system will do is give the person, a myoelectric hand user, the ability to sense when that hand is opening or closing, or it is picking up something, so force applied or sense of touch. So that is a completely novel thing that the system will be able to provide the person from the current commercially available prosthetic hands.
Okay. So from an engineering standpoint, how does this system work?
So as I explained, so the way the system works is there's two parts to it. One is that you have a prosthetic hand, and in that prosthetic hand, you have embedded sensors. So the sensors are able to give a signal out for the hand opening or closing, or they're able to provide information, for example, when the thumb is touching something or you have a grasp, so you get some pinch force information. So that's the prosthetic hand part. Now you take these signals that are these electronic signals, and these are converted to a series of stimulation pulses. And this pulse information is conveyed through a wireless link to a nerve stimulator that is implanted underneath the skin in the upper arm. And this is a wireless link, so there are no wires crossing back and forth. This nerve stimulator is connected to very fine wire electrodes, which are embedded inside the nerves in the fascicles. So what happens is that when the prosthetic hand opens or closes or grasps something, the sensor information is conveyed via the wireless link to the neural stimulator, and the neural stimulator will provide small electrical pulses that will stimulate the nerve. And when these nerves are stimulated, then the information will go to the brain, and the brain perceives that there is some sort of sensation, whether it's hand opening or closing or grip force.
Okay. So how are these electrodes for the system implanted into the residual limb?
So the way, as I said, they are very fine wire electrodes. So when I say fine wire, they're about the size of a human hair. So think of it as threading a thread and needle. So basically what is being done is that the nerves will be exposed, and inside the nerves, if you know the anatomy of the nerves, then the nerves that we have it's like a multi-stranded cable. So there are multiple, what we call fascicles inside one single nerve. So what will be done is that a needle with this fine wire thread at the end of it will basically sew the fine wire inside the fascicle. The needle will be discarded and the fine wire will be tacked, basically with sutures just tacked in there. And the fine wire is mostly insulated, and there's just a little portion that is de-insulated, and that's where the electrical charge can pass through from the stimulator to the nerve fibers. So by going into a very localized region, you can provide the electrical stimulation to a few fibers or a small volume of the fibers that surrounds that electrode point.
Okay. Can you explain to us a little bit of the science of how the electrodes communicate with the nerves in the arm?
So what happens is that, when if you have a normal situation, a physiological system, we have sensors for touch and for stretch of the muscles, etc. And these, when the sensors that are our physiological sensors, when they get activated, there's a whole neurochemical process that occurs, because of which there is kind of like electrical charge that travels along the nerve fibers. And in the case of peripheral nerves, all of this information then goes to the spinal cord, and then from the spinal cord it goes to the brain. So now in our case, when we have an amputation, the situation is that those sensors in the hand are missing because of the amputation. But you still have a viable nerve. So when you have a viable nerve, when you put these electrodes in there, when you stimulate with electrical current now, with effectively artificial electrical current, what you do is you do a similar thing. You so-called recruit, or you activate the nerve fibers surrounding that point where the charge is being delivered. Once you activate the nerve fibers, then the process is just like it occurs under normal conditions for physiology, that the nerve fibers conduct that electrical charge all along the fiber, goes to the spinal cord where more processing occurs in the physiological system, and then goes to the brain, and then the brain interprets the data.
Okay. So what type of UE amputees would make the ideal user of this technology?
So currently, the way we have it designed is for a unilateral transradial amputee. And so because of the way we have got the electronics from the prosthetic hand to be processed and to be wirelessly communicated to the person, there's a little box that will go into the frame of the prosthetic frame. And so we need a little space between the prosthetic hand and the end of the residual arm. So that's why we're looking at a transradial amputee. The implant will happen in the upper extremity part. But in general, if you look at it, what we would need is upper limb amputees who are those would be a good fit are those without denervation of the residual limb. So remember I said that the nerve has to be viable. And there should also be no neurological conditions that affect the motor or sensory function that would interfere with the use of the residual limb as well as with the intact hand, because we want the person to be able to use both those hands. And then as it is currently designed, it would not be applicable to people with shoulder disarticulations.
Okay. How many UE amputees would be involved in your first clinical trial?
So we are approved by the FDA for an IDE to do studies on 6 volunteers. We will start with 2 initially.
Okay. How long will this initial clinical trial last?
So the whole trial is designed to be for 2 years. It is in 3 phases, and the first phase is for 3 months, and it has many in-laboratory sessions. After this, we expect that the users will be able to take the system home and use it on a daily basis at home, and they will come back 1 week a month for about another 3 months to the lab, and then they will return about once a week every 3 months till the end of the 2-year time period.
Okay. What are your expectations for this clinical trial? What what do you hope this will prove?
So we've got 3 goals that we want very specifically to be able to answer after the clinical trial. First is we want to document and evaluate the performance of the implanted electrodes and the electronic system and get a good set of information on that. Second is we want to compare the motor performance of the UE amputees when they are using the neural enabled prosthetic system with neural stimulation and without neural stimulation. So with sensory feedback and without sensory feedback. We want to compare the motor performance. And then thirdly, we want to get information regarding the basic safety and efficacy of the system.
Okay. So I saw in a video about the system where the hand was able to pick up a grate. What are some of the examples of how you expect this technology to help amputees out in their everyday lives?
Yeah, so that's an example of what might happen in everyday life. We want them to use it on a daily basis, and we will ask them to wear some kind of movement monitor like Fitbit, so we can assess what these sensations do for greater usage of the prosthetic limb, for doing bimanual tasks that you might do in at home, picking up things that require both hands, not just one hand, and that require you to know how much load is there in one hand so that you have you balance your left and right hand's forces when you pick up something. So things like that, which it's not just sitting in a lab environment, picking up or just touching somebody or feeling somebody. So things that we don't even think about it when we do things. We hold an apple, cut with a knife, we are putting pressure on it. How much pressure are you putting on it? So that kind of activity of daily living, we want that to be the natural use of things that the people choose to do those kinds of activities by themselves.
Are there presently any limitations to what you expect the system to be able to accomplish?
There are some things that we don't know yet. We don't know how well they will be able to distinguish different sensations and the gradation of sensations. So, for example, if you think about the cochlear implant for the deaf, how well do they interpret sound when it occurs? Are they able to, interpret the different timbre and tone, etc., of music? So here is a similar situation. We don't know yet how well they will be able to differentiate different levels of sensation, combination of different things. For example, you are opening your hand, you're squeezing you're squeezing something. There's also your hand, closes and your fingertips are squeezing on it. How will people perceive those two things together? We don't know that yet. So these are things that we will have to figure out what happens. And also, as you know, the prosthetic hands, with the control itself, they have limitations. There are few hands with articulating fingers, others don't have articulating fingers. So the motor control part itself has got limitations to it. So, so those limitations of how all of that will get tied together, we are not 100% sure.
Okay. Once this clinical trial is complete, what is next for the NEPH system?
So once this feasibility trial is complete, we will work towards a bigger clinical trial so that we can move towards commercialization. And then at the same time, we will also be considering how the system could be applied to a different population. For example, for people with lower limb amputations, or people with, the surgical approaches will have to be changed for somebody like with a shoulder disarticulation. So we would look at both of those pathways. But for the system as it is currently designed, it would be a larger clinical trial towards commercialization.
Okay. And I recognize that you're fairly early on in this clinical trial process. But if everything goes according to plan and the way that you think it should, how many years might it be before we see this system available for prosthetists to use with their patients?
Well, I hesitate to hazard a guess, but I would say maybe 5 to 8. So if we think about this as being 2 years and another few years for another clinical trials. So one thing to remember is that the system is designed to work with multiple prosthetic hands. So if different vendors of prosthetic hands would sensorize their hands, put sensors in them, and then they give us access to the output from them. We have the capability of interfacing them with our system, and FDA has given us an approval such that our system can work with this appropriate interface with multiple different. We could swap out that prosthetic hand, so that makes the pathway towards commercialization I think a shorter pathway, because the implant part would be basically the same.
Okay. I've been talking today with Dr. Ranu Jung, the Chair of Biomedical Engineering at Florida International University. For more information about the neuro-enabled prosthetic hand, visit www.fiu.edu and type neuro-enabled prosthetic hand into the search box at the top of the page. And of course, we will provide links to all of the videos and pertinent information on our website and in our show notes for this episode on iTunes. Dr. Jung, I appreciate you taking the time to join me on AmpLife. It has been educational and informative.
Thank you for giving me this opportunity.
Absolutely. Thank you so much. You've been listening to AmpLife, the #1 podcast for amputees, hosted by an amputee, and brought to you by Dilatory Orthotics and Prosthetics, located in Pittsburgh, Pennsylvania. If you've enjoyed today's episode, leave us a review on iTunes or give us a like on Facebook. I'm the Brian Moe. I invite you to visit our website, www.amplifepodcast.com, or check us out on Facebook at AmpLife Podcast.